All right, so from this video, the next not couple, several videos, we're gonna look at different types of op amps, okay, which can serve as modules, okay, you could say for in different circuits. Basically, they have a purpose of their own, okay, each of them depending on what their configuration is, and using that we can basically achieve some kind of effect, okay, or some kind of amplification. Obviously it's an op amp, uh, of some voltage or voltage difference in our circuits, okay. So the first one we are going to look at, the first model you could say, is the inverting op amp. And to be honest, this is not actually something new if you have been watching my previous videos, because the only op amp problem we have been doing is this was actually an inverting op amp. As you can see, the configuration and everything, it's all the same. It's just that we used resistance values here instead of the general symbols. So if you're in a hurry to find the general formula, you could just uh, substitute the symbols for these resistance that need to be done. But if you can stay here, so I hope and I do hope so, because we're gonna learn some more about these things. Let's actually get right into it. Okay, so um, again, the goal here is actually to find the closed loop gain. Okay, so v output divided by v. Well, see, it's v. Yeah, so I think I should address this. A lot of people, I guess, call it v source, or again, it's can call it v supply. But anyways, it's really the same thing. Just I think there's really like the same kind of divide here as the zigzag resistance and rectangle resistance. Anyways, let's not waste time here. Uh, so this is the same node. This is the ground, and this is my a non-inverting input. So this is V2, and we see that this is equal to 0. This is the ground basically. So if this is 0, and again we're assuming that this is an ideal op amp, this is also going to be 0. So my V1 um, V1 is also going to be 0. Okay, for this whole node. Okay, this whole node is basically my V1. So this is V1 is equal to uh, oops, this is equal to 0 volts. All right. So if that is true, um, and another thing, okay, if we apply KCL here, if we apply KCL on this node right here, okay, this node right here, okay. So let's consider this current entering, this current exiting. Okay, so let's see. Let's consider this current exiting. Okay, and let's say this. Whoops, no, not that one. Oh man, uh, I seem to be too much in a rush. Definitely shouldn't do that. And we also have this current which is exiting. But the thing is, this is an ideal op amp, and we know that the currents entering each of the inputs, they're equal to 0. Okay, they're equal to 0. So that's why this is going to be 0. This current is going to be 0. So we don't need to consider that. The current entering here, this node, is going to be equal to the current exiting. So this one, this current which is exiting, and that's 0. So don't need to count that. So um, if we write our KCL equation, we get, let's see, current entering. So this node, the potential of that is Vs. So this is the ground. Then you have a cell. So you could say this is a super node. So this is Vs. Anyway, so this is Vs and this is 0. So the voltage difference, Vs minus 0, and the resistance between them is R1. So the current here is Vs minus, should have done this in blue, but anyways, divided by R1. Okay, this is going to be equal to my current which is exiting. Okay, the voltage difference here, need to consider the voltage difference from here between this and this. So and this is uh, you know this is the same node. Okay, this is the same node. So the value here, the voltage here is going to be V sub O. So the voltage difference is 0 minus V output and divided by the resistance, which is R sub F. and it's the F is for feedback, so it's the feedback resistance. That's why it's like that. That's the symbol. So here we have, whoops, no, not that, zero. Okay, zero minus V output. We need to get the order right. The currents in this direction. That's why this minus this. Okay, uh, the current flows from high potential to low potential. But anyways, so this is we have. Oops. Okay, so yeah, that looks good. All we now need to do is simplify this a bit. Okay, so it's pretty easy to see the zeros. They don't really matter, and we can divide by Vs. We can divide by Vs and multiply by R sub F. So we get V naught divided by Vs equals negative R sub F, okay, divided by R1. Okay, so this is my closed loop gain, and for applying this, okay, for applying this op amp in any situation, most people like to rearrange this equation and write it as V output as a function of the your source voltage or your supply voltage. So if we can do the same too, so this is this is basically your formula, okay, for the inverting op amp. This is the output. Oops, this is your output as a function of your input, or actually your source. A lot of people do actually call this the input voltage, but I'm refraining from that because it's just to not confuse it with the op amp inputs. Yeah, so that's why I'll refrain from calling it input. So, anyways, yeah. So this is basically uh, your okay. So, well, we can see here this is your formula for the inverting op amp, and it's inverting because, well, the resistances are positive. This is so we can see that your negative sign here is certainly, it's definitely going to invert the polarity of Vs. Okay, V output is going to have the opposite polarity, okay, compared to Vs. So that's why it's an inverting op amp. All right. Um, we got the formula. Let's actually apply this to a problem which is well, it's going to be the same type obviously because it has to be an inverting op amp. But at least let's change up some things, not just keep doing the same or same 10 kilo ohm 20 kilo ohm problem. So here, suppose say I have let's see, let's see, this is 50 megavolts, let's say. See, this is 40. No, let's say this is 4. So this is 4, 4 kilo ohms. Oops, let's see. This is your op amp. This is your, oops, is this here? Okay, and let's see here, and this is your ground. Okay, and we are not done. We need the feedback resistance. Let's see. So this is, let's call it. Let's see, this is 28 kilo ohms, and this is minus. This is plus. Okay. If the signs here aren't given, assume that the top one is your inverting input and the bottom one is your non-inverting. But standard problems do have the signs given, okay, or at least we can hope so. So uh, yeah, and this one is 10 kilo ohms. Okay, no, 10 ohms. Let's say. So what we need to do is find the current through this resistor. Okay, find the current through this resistor. All right. And if we like in the last video, suppose if with the knowledge of the last video, um, if we just had this problem, uh, you know we'd be able to solve it, but we'd be going about it in the way that we deal with any ideal op amp. Okay, but actually, after knowing about the inverting op amp, it's actually become much simpler for us because this right here, okay, this portion right here, so you need to see this carefully. This portion right here is basically an inverting op amp, right? This portion is basically an inverting op amp. Okay, just we need to be a bit careful when we try to see which op amp it is, because all the conditions need to be met. Like here, this is one really important condition. Okay, that your non-inverting input is actually connected to the ground. Like you cannot have some, suppose say this is 1 volt right here, so you could not have a cell like that. This would actually be against our conditions. This wouldn't exactly be an our inverting op amp anymore. Okay, so we need to be really careful that the configuration, okay, the circuit matches this one. Okay, so and if it does, and we see that it does, there's nothing different, only we just have some values. Okay, uh, we can say that this is an inverting op amp, right? So this is an inverting op amp. After careful consideration and inspection, we can say that this is an inverting op amp. Okay, and if it is so, what can we do? Well, we can, so this is basically your ground. This is basically your ground, and this is basically your output, right? So you'll have your output voltage right here. What we can do, we can easily find that, right? Because this is an inverting op amp. Okay, so we can easily find this. And see, if we just have the, then that would give us the voltage difference across this 10 ohm resistor, right? That can easily and then we can easily find the current. So let's do that. Let's find V sub O first. Okay, so this is going to be equal to negative our feedback resistance. So this is our feedback resistance. As you can see, it's slinged over the op amp. Okay, so this is our feedback resistance. So I'll write 28k. I'll write 28k. Okay, um, I can write ohm too. Yeah, so no need to be lazy. And divided by our this resistance right here between the non-inverting the inverting input and this cell, okay, or the supply. So this is 4 kilo ohms. We multiplied by our source supply. Okay, 50. And yeah, I also am kind of afraid of saying supply, because please don't confuse this with the op amp supply. Okay, that's not being shown here, and we aren't really concerned about that. Definitely the supply I'm saying over and over again is not the op amp supply. Okay, so it's this supply. Okay, the circuit supply, you could say. So it's 50 millivolts, 50 millivolts, 50 millivolts. All right. This is going to give us the kilo ohms cancel out. This is minus 7. Okay, so minus 7 into 50, it's minus 350 megavolts. Okay, that's minus 350 megavolts. All right, wait. Okay, that's minus 350 megavolts. Okay, so this is minus 350 megavolts. So what we have here, on two sides of this resistance, this is 0 volts. This is minus 350 megavolts. Okay, and as we know, current flows from low to high potential. This one is lower. The current is actually going to flow here, okay, in this direction, and the value of that current is going to be it's going to be I equals, let's see, 0 minus 350. Actually, I'll convert that to ohms. Okay, so not ohms, sorry, volts. So 0.35. Okay, uh, that's basically 350 megavolts. Volts, and this is divided by your resistance, which is 10, as plus, and yeah, this is 0.035, 0.035 yeah, amps, or you could say 35 milliamps. Okay, all right, so that's my answer, and we obtained it pretty easily. We didn't need to go through the whole process about uh, you know uh, figuring out node voltages, or applying KCL for using the ideal op amps, ideal op amps to, conclusions that we got, etc. You know what I'm talking about, right? I don't know why am I starting so much. So it was much simpler because we knew the configuration and the formula for the um, inverting op amp, right? So, and also, yeah, I really don't want to extend this any more than it has to, but let's just do one more thing, and this is kind of like me trying to convey the essence of circuit design. It's like most, what happens is you need a, you need something to do something. You know you know your aim. Okay, you have your goal. You just need to um, make a circuit that achieves that goal. Okay, might sound obvious. Suppose say I have a supply here. I have a supply here, and let's say this is 5 volts. Okay, this is 5 volts, and what I want is on this end I have some. I have a, let's see. I have a resistor. Okay, I have a resistor. Let's say it's 2 ohms. Okay, let's say it's two ohms. All right. Oh yeah, before moving on, I'll just need to I just really need to clarify one thing. A lot of you might be thinking, and you know this you really need be needing to think very deeply about op amps and all. If this thought did come to your mind, is that when I came up with the ideal op amp conditions or assumptions, I assume that this norm for the all the other resistances kilo ohms is on that scale, but you see that I'm using like 10 ohms and 2 ohms here, so that's kind of a contradiction, right? And actually no, because um, this is actually not part of the op amp circuit per se. Okay, the op amp just really works by itself. This unit just works by itself, and this is just some resistance that's just taking the output voltage. It doesn't really affect the op amp's operation, all right? So this kind of like independent, just takes the output voltage here, and that doesn't really that doesn't really hamper anything. All right, so let's not extend that. And okay, so let's okay, so yeah, my as I was saying, my purpose is, what I really want is, um I want a zero point 0.5 milliamps current here. Okay, I want a zero point 0.5 milliamps current here. I have this cell given. I just want this current here. Okay, wait, not milliamps. Sorry, not milliamps. I wanted the zero point 0.5 amps currently. Okay. Now I know what a lot of you smart people might be thinking, and all of you are really smart. Okay, is that we can easily, okay, so one thing is, the what's the voltage across this? What's the voltage across this? This is going to be 2 into 0.5. It's basically 1 volt, right? So yeah, it would be valid, really would be valid, if you use some resistance in series and use your voltage divider law to get this, okay, to get 0.5 amps here, or this required voltage here. You actually need to reverse connect this cell to the series combination, but that doesn't really, it's not really something difficult. Yeah, I know you can solve it that way, but as you know, we are doing op amps, so I really want to use an op amp, specifically our inverting op amp, to do this. And this is actually perfect for an inverting op amp, because as we can see, our voltage actually it's plus here, minus here, so you can see the polarity being inverted from what it was here, right? So using an inverting op amp would actually be perfect here. Okay? Using an inverting op amp would actually be perfect. So let's see. Let's do let's just draw our inverting op amp. So we have this resistance, we have the op amp right here. Let's see. um yeah, so that's kind of, so we have this, and we have, okay, I could even connect it here, but anyways, so the thing is, we just don't know the resistances yet. Okay, and for that, what we'll actually use, we do know the output voltage, right? We do know the output voltage. If we consider this to be the ground, this is going to be, you know 1 volts is in this direction. This is actually negative 1 volts. Okay, It's actually negative 1 volts. Okay, so that's the output voltage, and our input is 5 volts, right? So Vs, it's 5 volts. All right. So let's see what happens. Let's actually plug these in our formula right here. So what we have is, let's see. Uh, okay, so we have, let's see. Mm, V naught by Vs. Okay, V naught by Vs. We do know that this is equal to negative R by, R sub F divided by R1. Okay, but what's V naught by Vs? That's just equal to, so if we write this, so R sub F divided by R1 is equal to negative. Okay, so V naught, as we saw, is negative 1. Okay, it's negative 1 volts. So it's negative 1. And this is, Vs is 5 volts. Vs is 5 volts. This is, so the negatives cancel out. We get 1 by 5. We get 1 by 5. Okay, and I did choose this example particularly to show that an op amp's amplification doesn't always need to be, the magnitude doesn't really need to be more than one, or the op amp doesn't necessarily have to increase the size of the voltage. It can also decrease it. Okay, amplification in general can be an increase, an increase, okay, or a decrease too, okay, as a factor. So with that out of the way, we have, so we have this, we have R sub F divided by R1 equals 1 by 5. And you might be thinking, okay, so how do we find the two resistances? There's actually no like unique solution to this. Okay, and we don't really have any more information. There's really no unique solution to this. We would just need to use some suitable resistances that meet this criteria. Okay, so this is the criteria. There is no unique solution. I just need to find some resistances that are suitable for our purpose. Okay, like in real life. So let's, as I said, the resistances here should be in the order of kilo ohms. Okay, this is part of the op amp circuit. So like if this is, if R sub F, okay, so the ratio between these two is 1 is to 5. So if R sub F, okay, let's see, we'll write some, I'll write some possible ones. um, why am I using this color over and over again? So let's see, on one side let's have R sub F, on another side I have R sub 1. You could have a lot of possible answers here. Okay, this could be 5 kilo ohms, and that would be 5 times that, 25 kilo ohms. This could be 10 kilo ohms, and as you know, this could be, and this would be 50 kilo ohms. Then okay, so these are sets of possible answers. You kind of have an infinite number of them. We should just use what's suitable for us. So suppose, say you have some fixed carbon resistance on hand. So let's see, so this could be, as we saw here, one possible solution set, you could say, is this is 5 kilo ohms. All right, um, and this is 25 kilo ohms. All right, and yeah, that's that. So that's, I think, all that we needed to discuss about inverting op amps. We saw how it works, we saw the formula, we did some problems, and we saw how this could be used in for one possible application. Although the best solution for this application is actually just to have another resistor in series and using the voltage divider rule. But anyways, that's all file and well. So that's the end of this lesson, and study smart.